So let's make our own artificial intelligence. You find it here, go to ML100, and you can make your own in Colab. So you open Colab, which is Google's free Python environment, and make a new notebook here. And the first thing is put in this code. This code just imports the library called TensorFlow, which is the one we're going to use to do machine learning. Just make sure that we're able to import it and see what version it is. Not that we care what version it is, I just want to make sure it works. Okay, so it prints out a version number, so it's working. Now, this is what artificial intelligence can do. Suppose you measure something, and I used to do this. I used to be a research scientist. You would measure something, and then you would try to fit a curve through it to explain it. So you have X and Y. This might be, say, the temperature of something, and this might be the pressure of something. So you notice I've measured -1, 0, 1, 2, 3, and 4, and this is the output. So you notice when the X goes up by 1, Y goes up by 2. And that seems to be a consistent pattern. X goes up by 1 here, Y goes up by 2, and when X is 0, Y is -1. So the mathematical relationship is Y is 2 times X minus 1. Now this is what a human is typically needed to do, to look at something and deduce the pattern. And what we do in old-fashioned programming is we would program this equation into the computer. But machine learning will learn just from the data. It will do that deduction. And this is the code that does that. And it's going to model it with one neuron that can do a linear relationship on the input. So in comes X, it's going to multiply it by M and add C to make Y equals MX plus C, and it's going to learn these two values. So I enter a block of code here, and it doesn't take very many lines. These are the input data, X and Y, and then it will fit a model and predict the value for 10 as a test. So what it's going to do is go through a bunch of epochs. What this is doing is something called gradient descent. It guesses at those parameters and just randomly measures the loss. Now the loss is the difference between the prediction and the right answer. And so if I can get this thing to scroll up to the right place, maybe this will work. Yeah, it does. All right. The loss started at, I'm still having trouble. There we are. The loss started at 0.5, and then epoch 1, epoch 2, it moved to make it smaller, 0.56, 0.55, 0.53, 0.52. You see, it is taking steps and making the loss smaller until after 500 epochs of improvement, it gets to the point where the loss is extremely small, like 10 to the minus 5. And when it's done, it predicts the value for an X of 10. It predicts a Y of 18.98, and the right answer is 19. So it learns very well. After 500 epochs of improvement, it gets very good. And if you want to see what it learned, you can print out the weights. So this one will do the same fit, but print out the results, print out the resulting weights. So I'm going to delete the old data, put in the new code, and run that. All right, and there it goes. There goes the loss getting smaller and smaller. And when it's done, it prints out an 18.9. That's the prediction for X equals 10, which should be 19. And here's the weights it found, minus 0.99 and 1.99. And the right answer is 2 and minus 1. So again, it got very close. So it's good at fitting this. Now we can try learning with errors. If we add some noise to the data, then it won't be able to fit it perfectly anymore. So I go back up. Okay. And instead of those Y's, I'm going to use these Y's that have added a little noise to them. And I'll put a pound sign in front of that line to comment it so it doesn't have any effect. Now all the numbers have been moved a little bit, so they no longer perfectly fit on the curve. And here it goes. The loss is getting down to 0.05, 0.04, 2 below 4. Not as small as before, but still pretty small. And again, it learned the values 1.99 and minus 1.00, very close to the right answers of 2 and minus 1. So it was able to tolerate some degree of error. Now, if we give it a different curve, this is a parabola, not a straight line at all. And since the neuron only has a linear relationship to the input data, it can't really fit a curve very well at all with just one neuron like this. So it's going to have difficulty fitting that data. So when I run this, the loss is 875. The loss is going down, but it doesn't seem to be able to get the loss much below 4. And so the prediction is strange. The values are strange. It's not very good, as you'd expect. So anyway, we can fit a complex curve and we can print out the answer with a bit more code here. So I want to make a new notebook for this. I'm going to move to trash and return to Colab and make a new notebook. And run this one. This one is going to print 0.1 times x times cosine of x. So it's going to be a wavy curve that gets bigger as it gets further away from 0. So it's a much more complex curve to fit. Okay, here it goes. Now this model doesn't have just one neuron. It has one input neuron and a layer of 64 hidden neurons and a second layer of 64 hidden neurons and one output neuron. So that's a total of 4,355 parameters. The quality of a machine learning model is rated by the number of parameters. The Google Bard you're using has about 1 trillion parameters. The straight line had 2 parameters, and this has 4,000 parameters, so it's in between. It turns out that is enough to do a pretty good job after 100 epochs of training. Here's the answer. The blue dots are the input data, and the red line is the curve that was fit through them. And as you can see, it did a pretty good job of fitting it. So there are a few flags to find here by modifying it and trying different versions of it to see how it fits. And you can play with fitting curves. And there are a couple of other ones down here. Here's one where you get to do computer vision, which is very fun, I think. This uses a well-known series of images that are from fashion. So you have each image is a 28 by 28 pixel grayscale image, and it's sorted into categories like t-shirt, pullover, dress, coat, sandal, sneaker. And your model is trained on the input image to take all the pixels, then have a layer of hidden neurons doing the calculation, and then sort it into the probability that it has each of these outputs. And you can train it, and it can learn to do that pretty well, up to about 90% accuracy. So it will get it wrong about 10% of the time, and you can examine and see which ones it's getting wrong. Like this one here should have been category 7, 0, 1, 2, 3, 4, 5, 6, 7. It should have been 7. But the model thought it was only 27% chance it was 7 and a 72% chance it was category 5, so it got them confused. And when you print out the picture, you can see why. It looks like this, and it couldn't tell if that was a sneaker or a sandal, something like that. So it's understandable, and you can train that model and see how well it works. This model has 101,000 parameters. And there's another one down here that I was really amazed at when I found this, de-blurring images. This is what you see in cop shows on television. They have a blurry picture and they run it through some computer system that sharpens it up, and that's what this does. There's a database of blurry and sharp images you can get online, which are real images taken with a variety of cameras and blurred. So you have full color images of something and then a blurry version of it. And you train the model to practice de-blurring images, and then you run it to test it on an image it has never seen before. And if you train it for only 5 epochs, then it is terrible. This is what happens when it de-blurs an image. It just turns it into garbage. But if you train it more, If you train it for 100 epochs, that will take about an hour and a half. But when you're done, it will actually get pretty good at it. So here's the blurry image, here's the sharp image, and here is the de-blurred image, which, as you can see, it has removed some of the blur, and it has never seen this image before. It's just learned the idea of de-blurring images. And that, by the way, is how online computer vision works, like Stable Diffusion. This is the online image creator, where you can get anything you want by just describing it with text. So here I can say a dog riding a bicycle in the style of Picasso. And it will generate the image. And there they are. You can get anything you want. And the way this works is unbelievable. I learned this from the Google training course. The way this works is it finds some real Picassos and it practices 1,000 steps. It adds blur to them, and then it practices de-blurring the Picassos until it's good at that. And to generate these images, it starts from random noise and it de-blurs it in the style of Picasso to create these images. That's why it can create a bunch of them, and they all come out different, but they all have the style of Picasso. So I wouldn't have believed that would work, or that it was cheap enough that you could afford to give it away for free, but it is. So that's how these things work, and that's why they call it Stable Diffusion. It works by starting from noise and de-blurring it. So try some of that stuff if you like.